So today we have Marat Freytsis from Rutgers talking to us about effective uses of quantum computing for higher energy physics. Marat did his undergrad in Cambridge, then a PhD in Berkeley, postdoc positions at Harvard and Oregon, and now at Rutgers. Yeah, Rutgers. So Marat, take it away.
Great. Well, yeah, thank you for inviting me and me here. Yeah, so this is some work I've been doing for the last year and a half or so with some folks in UC Berkeley and Lawrence Berkeley Labs, kind of setting up some of the groundwork, I would say, for what a quantum simulation of high energy processes would look like using quantum computers. Setting up the groundwork in the sense that, like, we are, of course, like, ultimately what we would like to do is be able to run some sort of simulation of quantum field theory on a quantum computer at a resolution where we're able to say something interesting about real world physics, the kind of non-perturbative real world physics that we don't have any way of accessing any other way. But of course, we're nowhere close to that in terms of where the quantum resources are right now. So I think some of the efforts that are worth thinking about are just setting up the basic formalism for how such calculations would work, which that doesn't really exist beyond its very barest outlines. And also thinking about, given the minute kind of resources for quantum computation available in the real world, how do we most efficiently package the part of the calculation we want to do in the minimal amount of resources so that we can get to them faster down the line. So kind of just to motivate the big picture here, oh, what is, I can't do that. Oh, here we go. Okay, let me see if this works now. Okay, so to truly understand a given field theory describes data at some, let's say at a high energy collider like the OHC, what we need is to connect theory and data. That part is obvious. From this, we need some way of going from the formal description of our theory to, ideally, if we want to predict every single aspect of what we see, to fully exclusive events. And let's say kind of like one of the holy grails I can imagine of high energy phenomenology is to have some sort of end-to-end full simulation of scattering processes in high energy collisions, where we start, as I said, with the specification of theory, and we see what happens, exactly what happens in some sort of experiment that we run. Or to say it in slightly more formal ways, the dream, I think, from this picture would be to literally compute the full S matrix for whatever you specify the initial state, and for whatever final state you might hope to measure. Okay, so in other words, let's say kind of we're talking about the LHC, create an initial state with 2 protons at some time minus t, actually evolve with the full Hamiltonian theory from some initial time to some final time, and then perform a measurement of some final state. Oh, now we'll kind of say some kind of trivial points maybe. This clearly requires quantum physics to do this exactly. It's not even remotely feasible to do this using classical computers, because we're talking about quantum field, we're talking about an infinite dimensional Hilbert space. If we're doing this exactly, there's no way of storing that state. And if we could do this, it would of course revolutionize what we can probe using experiment and how we compare that to data. Yeah, so just with that motivation, this is going to be kind of a brief outline. I'm going to talk about how we would do these dynamical S matrix calculations on the lattice, and the reason for that, with the goal of putting it on some sort of quantum computer. Then I'll talk about how effective field theory gives you a way of isolating the parts of this calculation that are actually worth doing using quantum resources. And I'll demonstrate kind of a toy calculation we've done along these lines using actually already existing hardware that that IBM gives researchers access to. And then kind of I'll dive into some details of one particular aspect of this problem that we've looked at carefully, which is how to efficiently set up the ground states of the field theory on a quantum computer, because one aspect of this whole research direction is just a lot of the things that, for example, we just write down with pen and when we're doing pen and paper work. This is the ground state of such and such a theory. You have to figure out how to actually encode that in some number of qubits and do this in an efficient way, which scales well as their systems get larger and larger. All right. So the first part, just the basic formalism. So if we want to turn some sort of quantum field theory calculation into something that we can run on a quantum computer, what we need to do is we need to turn it into a quantum mechanical calculation that exists on a finite dimensional Hilbert space. Because the kind of paradigm, at least that currently exists for quantum computing, is you take some number of qubits and you entangle them together. And so the size of your Hilbert space is going to grow exponentially with the number of qubits that you have access to, but it is still always going to be finite. And so that's going to require both taking your fields and digitizing space in some way. But then on top of that, as long as you have bosonic fields, at every single point in space-time, you're going discretizing space. I'm going to try and be careful about this distinction. But of course, if you have bosonic fields at every single point in space, you still end up with an infinite dimensional Hilbert space. And so you need some way of digitizing that to have some approximation for it in a finite dimensional Hilbert space. So so we need to both discretize the position of our quantum field theory description and digitize the fields in such a way that all of this, as it fits in some discrete quantum mechanical problem. So this is, at least some aspects of this are a somewhat old idea. The discretization of space was kind of initially people started looking at this back in the early 70s. This was an alternative approach to lattice field theory. It was Hamiltonian lattice theory, where instead of Wick rotating into Euclidean space and discretizing all of space-time, you instead just discretize space and turn this into some quantum mechanical problem, some still quantum mechanical as opposed to classical problem, but one in which you might have hoped to make some progress by reducing it down with quantum mechanics. So that part we are doing the same way. You take space, you discretize it with some lattice of size n number of points in every single direction, assuming that there's and then assume there's some spacing that represents a physical spacing of the theory, and ultimately, because you'd like to make predictions about the continuum, you want some way to extrapolate whatever results you get as you take the lattice spacing little L to 0. Yep.
That's a really, really naive question. So what about this particular problem, and maybe you're going to get to this, makes it such that I really can take advantage of the quantum computing aspects of it? I guess I'm not still getting what, I mean, quantum computers can be great, and I understand they can do factorization, whatever, things like this. But what's specifically beneficial about a quantum computer for solving this problem as opposed to just a really good classical computer?
Well, yeah, so I will get to that in a
Okay,
second,
then I'll be
but I can give the lightning version the answer, which is that any sensible discretization of this problem, which is going to kind of give you a decent approximation for a field theory answer, is still going to require such a massive Hilbert space that there is just no hope of storing it using classical resources. And it's true that for certain questions, we have other ways of getting access to that problem. Like lattice QCD certainly allows us to ask various questions about the spectra of our theories by turning a quantum problem into a statistical sampling problem. And then you're not worried about you substitute for the fact that you don't have access to the full Hilbert space by just some sort of statistical physics analogy. But if you want to say something about an actual dynamical process, then there's no substitute for doing that with actual quantum mechanics. And if you try to solve that, if you try and encode that state using classical resources, it very quickly becomes something that it's clear we're never going to have the classical resources to encode in any conceivable future using classical methods. Yes.
Clarify. So what you are saying is that you need it for the storage and not for the solver. So for the solver, you could use a classical computer, but what you need is this.
No, it's both. I'm focusing on the storage just because it's it's easy to see. That part is quite easy to see. You just count the dimensionality of your Hilbert space and you see how that it grows exponentially, which I'll get to in just 1 second. But of course, implementing some operator on implementing any operation on an exponentially large space is also going to require an exponential amount of resources. So it's true both for state preparation and for state evolution.
One more question. Do you here's the number of spatial dimensions? You're also discretizing time, right?
We are not, no, we're not discretizing time. This is not the this is a picture where you take space, you discretize space, but you still have continuous time evolution. Well, I should back that up a little bit. There is, of course, at the end of the day, you're going to need to take your time evolution in some sort of number of discrete steps too. But unlike the Euclidean lattice gauge theory, there's no need for the time direction to be discretized in the same steps as the spatial directions. You can, at least in principle, you can kind of run that update step at whatever fine granularity that you need. Yeah.
So if you choose subspace of the infinite dimensional Hilbert space, will it cause the non-unitary distribution?
So
Yeah,
I'm
I
not
just
sure.
thinking of for Hamiltonian field integral some degree of freedom.
Oh, no, the evolution is always unitary sort of by construction because we're implementing unitary operators on some tensor product of qubits. In terms of the gut level, at the base level, what is happening here. The question is whether that particular evolution is a good approximation for the continuum version of the calculation where we're taking the size of the lattice to infinity while taking the spacing to 0. Yes, so sorry, yeah. So there's the discretization of space. But we're talking, you have to do that. But the additional ingredient that you need, as I mentioned earlier, is you need some sort of digitization of your field value so that ultimately the Hilbert space is finite. And so the Hilbert space, yeah, so you can kind of see here roughly it's going to scale. It's the number of digitized values that you need to encode at every single space-time point, and how many and you're going to need, n to the d number of those points for some d-dimensional lattice. And the Hilbert space of this entire problem scales exponentially in these quantities. Well, it scales exponentially in the number of points. But once you've done that, in some sense, the problem can just be reduced to matrix quantum mechanics. Okay, so just kind of some probably not too surprising statements. Of course, all of the continuous field theory operators we have can be written down in some sort of latticized form. So an integral over all of space can be turned to a sum over lattice operators, and all of your derivatives have to be turned into finite differences.
What is get x? What is get x?
Oh, that's just the position space picture versus the momentum space picture. I just mean that this is that any.
So it's not some particular state.
No, this is not some particular state. This is for any. Yeah, really, kind of. It's just. Yeah, this is shorthand. What I really mean here is that you turn some sort of field representation, which is defined as a tensor product of position space fields. There's a way of efficiently implementing Fourier transforms on quantum states such that you can turn that into a field representation, which is a sum over momentum eigenstates. For example, momentum eigenstates for the free theory. In a way that is, in a way that is efficient in the size of your system. Okay. So yeah, say some other probably somewhat straightforward things about this. The states now they are of course vectors in this finite dimensional Hilbert space, and operators become some sort of matrices that act on it. And in a lot of ways, the question becomes: is there an efficient encoding of these various statements that you can find, one that will scale nicely as your number of points or your number of points in space, or the number of points that you use to represent a field, the number of values that you use to represent a particular field at a particular point in space as those go up. And in this business, I guess I should say when I say efficient, what kind of this in the computer science sense of if I can find some way of doing this that scales polynomially in the number of qubits, then that is something that I will call an efficient algorithm. And if it scales exponentially, then that is not efficient, and that is not something that if the only way that you can do this is some way that's going to scale exponentially in the number of qubits, then effectively there's no point in doing this on a quantum computer because then the classical problem, the classical analog of doing this calculation is going to scale exponentially, precisely because that's how the Hilbert space scales. So yeah, so at that point the answer would be that there's no point in doing this on a quantum computer. You might as well just run a classical simulation. It'll be much cheaper. All right. So yeah, so I think this is just restating how you would do an S matrix calculation. So again, in this language, just in this finite Hilbert space language, you create some initial state vector. At time -t, you evolve this state forward using the Hamiltonian here of the tracking theory, and then you perform a measurement on the state, and by performing measurement on this state in kind of a quantum simulation parlance, what that really means is you figure out how to create the final state that you wanted, and then you literally run that circuit backwards. You essentially it's doing kind of algorithmically exactly what we formally do when we do a measurement, which is just you have creation operator and annihilation operator is just a Hermitian conjugate of that. And as a quantum calculation, that just means running the exact same unitary transformations, just running them in the reverse order. People refer to that as uncomputing something. Right. So yeah, so why bother to do any of this to begin with? I think probably this is how we phrase it. Let's say that we want to simulate something at the LHC. So as a kind of rough hand-waving estimation, the energy range that can be described by some lattice is given by the 1 over the total lattice size. It's energy between 1 over the inverse total lattice size and the inverse lattice spacing. So let's say kind of we want to simulate everything down from the highest energy particles that the LHC produces to, let's say, the pion mass. So 100 MeV to 7 TeV. Putting this into the range I gave here, what you're going to need is something like 70,000 to the 3 lattice sites. So that's 10 to the 14 lattice sites. Let's say I need order 10 qubits in order to digitize. I picked 5 for reasons that are not terribly important here. So the dimension of this Hilbert space would be 32 to the 10 to the 14. So that's not infinite, but as far as computing resources, that's large enough as to be effectively infinite. So we're clearly never going to do this calculation. And we need some sort of way of taming things, and that is where effective field theory, the lessons that we've learned from effective field theory can come in to help. solid to help tame this problem a little bit.
Maybe I'll
yeah.
get it, but for a quantum computer,
Mhm.
the estimate would be 10 to the 14 instead of
Um,
32 times 10 to the 14.
yes, that'll be a part of it. Well, it would be, you take log base 2 of this to figure out the number of qubits that you would need to encode that. That becomes 5 times 10 to the 14. That is still a huge number. That is somewhere on the, yeah, I mean, that's essentially kind of a petabyte's worth of qubits. I believe within the last few years, we finally reached the point where we have classical memory resources of that size. So it's hard to imagine that we're going to have quantum memory resources that look anything like that, maybe for at least not for a long time to come.
But maybe smaller scale problems.
Yes, so on top of turning this, so first of all, yeah, in order to tame the exponential aspect of this, you would want to use a quantum computer. On top of that, you're going to want to cleverly organize your calculations so that you don't need to just stick literally the entire quantum field theory problem onto the computer in order to make progress. Yeah, I have a slide in a couple of slides that makes essentially this point, but I guess I already made it. Okay, so to simulate things, let's say again, the LHC requires several different energy scales for which we have different tools at the moment to deal with. So at short distances or high energies, perturbation theory works quite well to describe our hard processes. But then, of course, these evolve. Multiplicity goes up using, typically we model this part of the collision using some sort of parton shower Monte Carlo. And then, of course, all of those states themselves, at least when they involve QCD, have to have soft radiation hadronization that receives kind of large non-perturbative corrections or is intrinsically non-perturbative. And for that, at the moment, we have just various phenomenological models that we mostly just tune by fitting the data. But let's see, if we're talking about making sense of, I'm not going to say anything right now about the hadronization part of it, but let's say if we want to talk about the hard process and the part that is commonly described by parton shower, we can separate we can actually use we can separate the physics that goes into these into several different characteristic scales. The ones that turn out to be relevant when you just have a few hard particles producing initial collision is of course the intrinsic scale at which the collision happens, the hard scale. There's another scale which is associated with physics that is happening along particular kind of the direction, particularly highly energetic particles, and that is referred to as the collinear scale. When we're thinking about, let's say, QCD at the LHC, you can think of that as being roughly the order of the mass of the jets that get produced. But it turns out there's actually an additional scale in this problem known as the soft scale, which is given by a ratio of the jet and the hard scale, the collinear and the hard scales, which is the characteristic scale in which you need some other way to describe what's happening with the soft radiation in the problem. And there is already an effective field theory that's been developed to deal with precisely this kind of problem. It's called soft collinear effective theory. And what it does is it takes the fundamental fields of your Lagrangian and splits them up such that you have different fields for these different characteristic scales of the problem, and they don't really have to talk to each other other than through some matching coefficients that you compute. So yeah, so typically in this problem you have a collinear direction for each hard scattering you have a collinear field for each hard scattering direction, and you have a different soft field that describes just what the soft radiation is doing. Yeah, and the nice thing about these effective formulations is that they give you a way of, at the level of the Lagrangian, already splitting up this calculation into separate pieces that can be computed independent from each other. And so you can kind of focus, for example, if you want some other way of doing one of these calculations, then perturbation theory or some Monte Carlo simulation, you could focus on just that particular part of the problem instead of having to simulate everything. So kind of for jets at colliders, there's this kind of general form of factorization theorem that you can prove where overall the process turns into some convolution of a hard process, which different kind of contributions to that are only relevant around particular collinear directions and an overall soft radiation contribution. And the hard process, like I said before, we can usually compute quite well using just standard perturbation theory methods. It turns out, for kind of reasons I won't really get into, for reasons I won't discuss in too much detail right now, the jet contributions also typically end up being mostly dominated by perturbative contributions that you can also just compute using standard quantum field theory methods. And the part that is typically most challenging is to compute the soft contribution, which, as I said before, kind of lives at actually parametrically lower scales than the entire process itself. So for example, if I have a 1 TeV jet, which has a 100 GeV mass, then the soft scale is only 10 GeV for that process. That is the scale at which I really need to start treating the soft radiation in a kind of in a different way than I would in the perturbative process. Okay, so that already kind of buys me a significant reduction. Because now, if I say that I want to do a full intrinsically quantum simulation of that process, then now kind of I only need to go from 100 MeV to 10 GeV or so. So kind of in this hand wavy way that I said before, we've kind of gone from 10 to the 14 lattice sites that we need for a 3D simulation to about 100,000 lattice sites. So the dimension of that is still 32 to the 10 to the 16. That's still kind of close enough to infinite for the purpose of putting it on a quantum computer. But so it's impossible. So I think it's still impossible to do this calculation classically, or to imagine we'll be able to in the near future. But this is where this observation comes in. This was kind of a point that was made by Richard Feynman over 40 years ago. At this point, given that these are intrinsically quantum processes, it'd be interesting if we could figure out some way to kind of have a quantum mechanical computer that could do these calculations for us. And the thing that buys us here, sorry, I shouldn't have gone that far. Yeah, so, and kind of as Ken already said, what that's going to do is it's going to mean that instead of that those 10 to the 6th lattice sites, if we want to encode that Hilbert space into some number of qubits, then that is going to be something of the order of 1 million qubits, which is still far more than what we have at the moment, but is a number that you could imagine reaching at some point in our lifetimes. The people that are the people that are working on the hardware of this claim that this is something that we think we'd be able to achieve within the next decade or two. All right. Yeah, so we'd like to turn this into a problem for a quantum algorithm. And in fact, kind of one part of this was the key insight. Well, some of the first steps here were already taken in this, say, kind of pioneering paper 10 years ago by Stephen Jordan, Keith Lee, and John Preskill, where they wrote down the basic guts of the algorithms that you would need to simulate, to write down the simulation of scalar field theories in the language of quantum circuits. How you would actually decomposing things into some number of basic unitary gates, how you would write down a field creation operator, how you would evolve the Hamiltonian, at least in their broad details. So they did this in terms of they said kind of just how do you put like an entire S matrix calculation, at least for a scalar field theory, how you would write that down as a quantum algorithm. And so using kind of these basic ingredients, we want to isolate the part that would correspond to this effective field theory language that I sketched out for you earlier, the soft radiation part of this process. Okay. Yeah, I guess this is where I finally wrote down the number that we're talking about. If we encode this Hilbert space on qubits, you need, instead of 10 to the 14, which still seems like the type of space that we can't really imagine having. Instead, we put that on a much smaller number of qubits. Oops, sorry. Yeah. I've already said all these various statements that, over the past 15 minutes or so. All right, so, for those that are not familiar with this language, which I think is a lot of people in energy, I figure I should kind of give a very quick crash course on when we talk about quantum computing, so that the things that I say next are not going to be completely incomprehensible. So what we do is we represent every single state by some number of qubits in some state. Qubit is a two-state system. As physicists, I think we often want to think about that as like spin out or spin down of some system. But for quantum computing, people typically can just write this in binary notation. The qubit is in some linear combination of the 0 and the 1 state. So we operate on these qubits with various unitary operations. So some 2x2 matrix is just some sort of rotation that you make on the two-state system. So that is something that can be applied to a single qubit. On the other hand, an arbitrary unitary operation that involves more than two basis states, like for example, some 4x4 unitary matrix, necessarily involves a pair of qubits at least. And so as a result, it requires typically requires some sort of entanglement to be created between these qubits. It turns out that it's been proven that any arbitrary unitary operation for operating on any size Hilbert subspace can be built out of a very small number of basic operations, which essentially are the unitaries acting on single qubits at a time, and then a small number of controlled controlled operations, which are essentially kind of something like the following operation, which is you look at the state of one qubit. If it's 0, then you apply this unitary U to the other qubit, and if it's in state 1, then you do nothing, or vice versa. And it turns out that kind of as long as you have sufficient freedom in your one qubit unitaries, you can decompose the third large unitary into some number of these gates. Okay, so the reason to do this on a quantum computer, of course, is that on a quantum computer, in some sense, you can do many calculations at once. So in parallel doing this. So here's kind of a very toy circuit representing these kinds of controlled unitaries. Each line is a qubit. So let's say I take the first 3 qubits and I call that an index register I. So I imagine that kind of its state in binary notation encodes some number from 1 to 8. And depending on whether that number is, if the first qubit is a 1, then I apply this unitary U. If the second qubit is a 1, then I apply U squared. Third one, I apply U to the 4th. And if you think about what that does is it takes any state with index I and then applies to my final qubit Q the unitary U to the jth power. Which means that if I have a superposition of states, something that looks like this, then what I end up with is a state in which I've applied a superposition of all of the various powers of this unitary U applied to the final qubit. So in a sense, for example, because here I have my index qubits go from 1 to 8, in a sense I've done 8 calculations using only 3 fundamental gates. But of course, it was quantum mechanics, so I don't have access to the full final state vector. I can only do a measurement on it, which will give me one answer. And so I have to think carefully about exactly how to use this information, to use this parallel calculation in a useful way. Yeah.
Just a technical question on it. How do you actually technically make this matrix? Like the unitary matrix, what if, I mean, at the end of the day, there's qubits right there. Some
Yeah.
I don't know, some crystal or some atomic.
So,
crystal.
I mean, that is very hardware dependent, like, for example, the calculations that I'm going to show at the end that we actually ran on a kind of baby quantum computer that IBM provides for us. There, the qubits are encoded as I believe transmons in some superconducting state in an ion trap that actually I think sits in some ion trap in Oak Ridge. And what they do is they really have, by applying appropriate RF pulses, they can take each individual transmon and do an arbitrary, rotate, or they literally do X, Y, or Z rotations on the individual transmon qubits. So those are, let's say, the 2x2 unitaries. You can build that up through any combination of X, Y, and Z rotations, because those are the 3 generators of SU2. And then these controlled operations are a little bit trickier because they require some coupling between different qubits. And there, the basic operation that you can run, that they know how to run, is essentially you turn on an appropriate kind of coupling between 2 qubits, such that you apply what's known as a C0 gate, which is essentially, if one of the qubits is 1, then flip the up and the down, the 0 and the 1 indices the second qubit, and if it's 0, then do nothing. And that is the only coupling operation that they can run, which is precisely why it was so important, why the statement that I made earlier was so important, that it's known that any size unitary operation can be decomposed into some combination of 2x2 unitary matrices and some sort of entangling operation like this.
This control operation is non-unitary, right?
No, it is.
Because of if you first give it to 1, it will eliminate it, right?
No, if my Hilbert space looks like this C0 operation. This is a unitary matrix.
What's the previous slide? It was 0, 0 tensor product by you.
Well, so this is specifically 0, 0, 0 tensor product. Sorry, this operation I wrote down here is specifically 1, 1 tensor product sigma x, the poly x. What I wrote before was slightly more general. Yeah, I said this was an arbitrary.
Yeah, but this one is non-unitary.
This is unitary.
But
It's
he's
a
saying,
project-
I mean, if it's 0, then
Oh,
it's do
oh.
nothing, right?
Sorry, yeah, what I'm not writing here is +1 tensor 0, 0.
Oh, okay, good.
Yes, yes, so, sorry, you're right. As I wrote this, literally it's not unitary, but it is, yeah, it's kind of a standard notation where if you don't write an identity, it's assumed that it's that.
Okay, thank you.
Right, I just had a question about that controlled operator.
Yeah.
So the controlled NOT gate would be for specific unitary where you flip, if 1 bit is 0, you flip 0 and 1. But
Mhm.
that's a unitary matrix, that flip, but it's not a most general.
It is not, it is not. There is, yeah, I am kind of speeding through this, so I'm glossing over some details. There is a standard decomposition, which was worked out by Peter Shore and company back in the early 90s, where any gate like this can be written as a combination of, at most, 2 C0s and 3 1-qubit operations. Like 4 1-qubit operations. So yeah, so that is just, yeah, because that's a simple enough system where you can just prove that that's optimal. And so whenever people write this, what actually gets implemented in hardware is this decomposition into two C0s and assign the few 1-qubit operations. Okay. So kind of just to give you some intuition for at least an example of how this works and how it can do something, how these kind of basic operations can do something a little bit non-trivial. I'll show you this circuit. Probably doesn't look like anything to you right now, but you can see that all it is a combination of a few kind of there's a single 1-qubit poly X, and these other ones are shorthands for various kinds of controlled, once again, controlled NOT gates. Where if there's kind of two dots on a line, it means that it's a double controlled gate where the, for example, kind of in this middle one here, you only implement a NOT if Q2 is in the 1 state and W1 is in the 0 state. So let's say kind of I start with the following state. My W's are in the 0, 0 state. My Q's are in the 0, 1, 1 state, which in binary notation is just 3. What do? I apply the X gate to Q1 that changes one of the ones into a 0. I apply this C0 gate, but because it's controlled by 0, it doesn't do anything. Then I apply this reverse C0 gate, which because W1 is a 0, it applies a NOT operation to Q2. Then the next controlled gate does nothing because everything is in a 0 state. Then it changes Q1. Next gate does nothing, nothing. And so what do I end up with? In binary notation, I started off with 0, 0 with first the W's in the 0, 0 state and 3, and I ended up with 0, 0 and 4. And in fact, you can check what this is going to do for any combination of the Q register. And what this does is actually it's a circuit that's an adder body. It takes any number that you put in the Q register and it turns that into takes n and turns it into n plus 1. Yeah, nothing actually happens to the W qubits. They're W because they're word qubits. They're just scratched.
If it's 8, it will turn to 0, right?
Yes, yes, or 7 turns into 0.
Okay.
Yeah. Yeah, there are. Yes, yeah, because it has to be a unitary operation, so everything has to be invertible. There's no way of just like losing information by going into an overflow event. Okay, or for the reasons I said before, if there's some superposition of registers, then every single one is going to get shifted. Okay, so what do we want to do? What we want to do is we want some way to write down this SOP function that I mentioned before in this language. Okay, in field theory language, what I want to compute the SOP function is actually to compute what's known the expectation value of some number of a pair of Wilson lines. If I'm talking about, let's say, a SOP radiation from 2 particles that were created back to back. And so what I really want to be doing is I start off, I create a vacuum, I act with these Wilson line operators, and then I read off some final state. What does this look like on a lattice? On this lattice picture that I said before, I have a vacuum. Sorry, I guess I should go back up. This is Wilson line on a null direction, and so kind of in space time, I have Wilson line starting out with the origin and then heading out to infinity along some light cone. But as a process in time, what does this look like? I start off with the vacuum on the lattice. Then I act with one Wilson line, one direction. Then I act at the next point at the next point in time. I act at the next point in space with this field operator. Then the next one, the next one, the next one, and the exact same thing with the other Wilson line going off in the other direction. So together, what I have is just at different times implementing particular field operators at particular sites. It's really just it really is the dynamical picture of having this Wilson line in time spreading out. And if I discretize everything, it can all be written down as some number of field operators acting on the state at subsequent points in time, and in between each of these points in time, what I have to do is I have to evolve the state with the Hamiltonian for the same exact amount of time, because this is all happening along a null length cone. So it really is kind of an iterated operation of I create my state, I evolve it with the Hamiltonian, I act with these field operators, I evolve it with the Hamiltonian, I act with the next set of field operators. And I do this again and again until I've constructed my final state. And then I have to have some way of actually reading out the final state that I want. But one nice thing about this, actually, that's worth pointing out, is unlike a classical calculation where, of course, for every single final state that I want to read out, I have to do a U calculation. Let's say if I want some 3-gluon final state, I have to do the calculation for 3-gluon final state. If I want a 4-gluon final state, to read that out. Here, this evolution evolves to a state which is precisely a linear combination of every single final state that I can possibly get to from my initial state. So this part doesn't change, it's completely final state independent. And the only thing that I need to change about my simulation to read out a particular final state is just apply, uncompute the state that I want to read out at the very last step. Okay, so kind of in very kind of high level language, what I'm really doing here is I'm starting with some lattice, my lattice that I encode in some number of qubits. I act on that with a unitary operation that takes that from like the qubit 0 state, 0, 0, 0 state to a state that represents my quantum field theory vacuum state. Then I act on that with this combination of Wilson lines and Hamiltonian evolution. And then I read out some final state by running the creation operator for that final state backwards. And I read out the state of my qubits. And if I get all zeros, because I've uncomputed the state X, then that is telling me that I ended up in state X at the end of this dynamical process. And I do this, I run this circuit many, many times to get statistics, and the fraction of times that I end up with an all zero state at the end, that is telling me the fraction of the number of times that I actually ended up with the state X after running this particular simulation. Okay, so yeah, so this is kind of just saying again in words, whether as a list what I just said in words. So that the Hamiltonian, at least for scalar field theory, turns out is rather simple to implement. That the reason is that it has two parts, and these two parts are if you're in the momentum, if you're in the position basis, this kinetic energy operator is completely diagonal. If you're in the momentum basis, the momentum operator is completely diagonal. And the thing that takes you from one to the other is just a Fourier transform, which I said before is something that can be efficiently implemented on any combination of qubits. So implementing Hamiltonian evolution can actually be done quite efficiently by implementing the kinetic part. Let's say you start in the position basis. So the kinetic part is diagonal, so it's just a bunch of phase rotation that you apply to your qubits. Then you do a Fourier transform to go into the momentum basis. You apply a bunch of phase rotations in order to implement the kinetic part of the Hamiltonian, and you do an inverse Fourier transform to take you back into the position basis. And by alternating between these two several times, you can actually get a very good approximation for applying the exact Hamiltonian evolution operator. Yeah, this is essentially nothing other than the first term in the BCH formula. If you want to be clever and avoid and minimize the quantization, the discretization effects that you get from doing this, you can compute higher order terms in the BCH formula and just apply them in exactly the same way. Okay, and so all of this means that in data Hamiltonian can be implemented using resources that scale polynomially in the number of qubits, which, as I said, is what we call efficient in this business. Okay, so this is just a little graph to show you that this is a kind of a sanity check that we ran to show that we know what we're doing, which is to implement this Hamiltonian evolution using a controlled gate. And kind of you create some state, you evolve it, you uncompute that state, and what you get when you this calculation is kind of as a function of the amount of time that you run it for, it is going to give you a periodic oscillation with the period that's equal to the frequency of your state, sorry, the energy of your state, I should say. And so this is all this is saying is that like there was a scheme for taking these number of steps in the Hamiltonian evolution, where in fact, using a quantum simulation, we were getting exactly the energy that we wanted out of the undigitized theory, because you can do just a quantum mechanical calculation in this case, because the Hamiltonian is just that of a free scalar theory, and so it can be exactly solved.
This is the points are what you ran on the IBM.
So the line is the theoretical prediction. The points are what we got out of a simulation of the IBM quantum hardware. So because this was just a diagnostic graph, we ran a version of this on real hardware for calibration, but I'm not showing you that. This is just saying that like the circuit that we wrote down was in fact doing what we expected it to do, which was to give us just a sinusoidal variation with the frequency is the same as the energy of the state that we were producing, provided that you took the right number of steps. If you just try and do this evolution in one single jump, you see this is what you get on the blue line, and we can predict its behavior, but it's not actually what is happening in the field theory though. Okay, but then we wanted to kind of run at least some basic toy version of this calculation on real world hardware. And in order to do this, given how much is available, we have to make the problem very, very small. So this is very far away from the field theory limit, but at least it is an actual quantum mechanical system. We set up a system with 3 lattice sites in 1 dimension. And so what do you get really? You create a ground state, and then you act with the field operators for the Wilson line at the 2 states next to it, and then you stop. So that's it. It's not a very large exploration of space going on here, but it does something. And then at each, if you look at how close to these results come if you encode every single lattice site using 1, 2, or 3 qubits to the undigitized version where you actually have the full Hilbert space of a simple harmonic oscillator at each site. So these are kind of just some calculations of the eigenvalue, and you can see that already actually with 2 qubits per site, you're getting per mil precision on the first 10 or so eigenvalues of the system. With 4 qubits, you would already be getting 1 part in a billion precision. So at that point, kind of quantization errors are nowhere close to your biggest problem. But with just the point here being that you don't actually need that many qubits. So it was somewhat surprising to me in order to represent a continuous field with fairly good fidelity. And then, so this is again kind of the actual calculation we're trying to run. It turns out it's kind of cute. The lattice result can be computed analytically, and the answer can be represented exactly using coherent state formalism. And so we, in fact, had analytic predictions that we could compare against in terms of what we would expect to see in this case. And this is, for example, the answer on this 3-site lattice. We turn on some coupling constant between the scalar field and this Wilson line operator. We start off in the vacuum. You can see again, this is about what you would expect, which is if there's no coupling between the Wilson line and the field, then it starts off in the vacuum and it stays in the vacuum. As you turn up the coupling, the chance of ending up in the n=1 state of the lowest lying momentum mode becomes higher and higher. That kind of, we can compute this for being, in any excited state of the momentum mode or any combination of momentum modes. But this was just kind of the lowest lying excited state. So that's the one that I'm showing you. And this is what we expect to get. So this is the corrections from digitization, this is also just a theoretical correction, but one using simulation. If we encoded each field with just 1 qubit, so that you were only recording the 2 different field values per se. Unsurprisingly, not very accurate, but kind of qualitatively looking somewhat correct. But already with 2 qubits in this simple system, you're getting 4 field values per lattice site. You're getting reasonably good agreement with the full theory result of something within a few percent. Okay. So then, and then with by 3 qubits per site, then at least at the accuracy that I'm showing this, you can't really see a difference between that and the continuous calculation. So this is all theory predictions. Now we did this and we ran this on the quantum computer. Do that. Okay, this is what we would expect from the simulation, and when we run on actual quantum hardware, we get that for the vacuum to vacuum transition. So that doesn't looks maybe qualitatively correct. That doesn't look very good. But then what you have to realize is that there are all sorts of decoherence. Like these are very fragile quantum systems. There's all sorts of decoherence effects, and just in those few microseconds that it takes to run this circuit, there's already you can see a pretty significant chance of the system just evolving to some unexpected state and giving you a different answer. But it turns out there's ways to mitigate some of this through what is known as zero noise extrapolation, where essentially you introduce additional noise into the system. That is a scaled up version of what you already know is there. You see how much the signal degrades, and you try and extrapolate that answer back to what it would be in the zero noise limit. And when we apply some of these techniques to calibrate the system, adjust these raw results out, what you get back is this. This is actually, I think, pretty close. It's within a few percent of what we would expect. And these black points, I said, are coming from an actual, honest to God, 6 qubit system that that IBM has prepared for us. It's a bunch of qubits, like I said, sitting in a dilution fridge in Oak Ridge. And it's kind of neat that that we can write a quantum circuit, send it off, a bunch of ions get moved around in a trap, and 5 minutes later, we get counts that when we process them convert into this thing that is agreeing with the baby quantum field theory calculation that we did. Okay, so I guess before I go on, should I stop there and see if there's any questions? Okay.
Just quickly, Matt,
Yes.
that clock is fast, but maybe try to wrap up.
Yeah,
in 5 minutes.
I saw that I don't have that much time, so I might just not say very much about this last step, except just the following statement that in this previous case, because we were working on such a tiny lattice, I kind of skipped over the preparation of the ground state. And that's because we really just did it by hand. We figured out what the state was, and we decomposed it into individual kind of operations, not through any algorithm, but just by staring at the state and figuring out how to build it up through these controlled rotations. And you could do that for a small lattice, but it's going to be exponentially expensive on a large lattice. And so you need some sort of, if this is going to scale up, we need some sort of efficient way of building up these ground states. And at least conceptually, a method for doing this was worked out by Alexei Kitaev and John Webb in 2008, which essentially came down to the statement that a free theory ground state is really some set of correlated Gaussians, and these can be decomposed into using the LDL decomposition of matrices into setting up a bunch of one-dimensional Gaussian systems, and then applying a skew rotation in order to transform them. So both of these steps have, it turns out, it was proven at this time that both of these steps have efficient implementations in the sense of ones that scale polynomially in the size of your system, but no explicit algorithm for doing this was presented. This is something that actually we worked out, and we had a paper on this a couple of months ago. I'm going to skip over the details, but just the point is that we have algorithms with explicit circuit diagrams. We can tell you exactly how to prepare one of these states using these kind of basic entangling operations that I mentioned earlier. And the point is that while it has a large overhead for implementing it, once you get past kind of some reasonably small system size, the generic exponentially scaling algorithm is of course going to get far too expensive to imagine actually implementing it in principle, whereas these kinds of states are always going to take, maybe tens, maybe possibly hundreds of thousands of operations for any sensibly sized system, but not more than that. Similar thing for the state for the part about kind of rotating the 1D Gaussians into each other, with the end result being kind of this is how you would expect the generic exponentially scaling algorithm to scale the number of C naughts that you need, and you see it goes up very quickly with the size of your lattice. Whereas if you have these kind of efficient, clever algorithms for entangling things in parallel together, you get much better scaling with system size. Okay, so the general point being that by combining effective field theory considerations with quantum algorithms, we have the possibility of computing non-perturbative dynamics in quantum field theories of first principles. We're not close to being able to do that in practice, but at least we can start setting up some of the formalism. So making all of this scalable is going to require efficient algorithms, both considerations of efficiency, both on the field theory side of how you set up the calculation, and in terms of the actual algorithms of what you're going to run as a quantum circuit. And kind of, well, we showed that some of these relevant calculations are possible. A lot more work is needed in order to kind of scale this up in the real world. There's both kind of field theory questions involving how you extrapolate all of these results out into the continuum limit, and for more realistic theories, and there's details of there's various tweaks that we can do to improve the algorithms compared to what we're doing right now. And actually, I'd say various questions in terms of the fact that you're working directly with the Hilbert space gives you all sorts of freedom that you don't have in a classical simulation like that. You need to organize your calculation in whatever basis it is that it's most efficient. And so I think there's still, we did this in the way that is maybe most straightforward from the point of view of how we think about doing the calculation as a perturbative calculation. But I think that it's in no way clear to me that that is, at the end of the day, going to be the best way of thinking about how to implement this as a quantum algorithm. So there's certainly kind of room to think about alternative formulations, and some of this stuff we're already thinking about. Some of it is just a glimmer in our eye. But yeah, thank you. And if you have any questions, I'm glad to take them.
I have a question coming from ignorance, but it seems that the efforts are trying to calculate the time evolution through a Hamiltonian. But we know that in the end, like the most fundamental way of seeing the theory is through a path integral. In the sense that for non-abelian gauge theories, there's no notion of standard quantization, and dagger, and if one has the path integral, actually we have all the momenta of the distribution. Why the efforts of doing quantum computing come from defining a Hamiltonian, which is non-relativistic, and not trying to calculate somehow all the trajectories in the path in the space of for example, of fields or of positions?
Well, I would say that my answer is also coming from a place of ignorance, which is that this is the thing that the Hamiltonian formalism is the thing that most efficiently maps onto how quantum algorithms get implemented in terms of their basic fundamental operations. I'm really, I'm gluing unitary operation after unitary operation after unitary operation, and I don't know how to at least generically, how to take a path integral and convert it into the kind of language of, this is what you would do to manipulate an analog system of like a tensor of qubits. There are certainly, so the short answer is because this is the thing that I know how to map into the calculation that can be done. There are certainly things that are complicated by the Hamiltonian picture, as you say. Like right now we're currently thinking about the details of just digitizing abelian gauge theory, and that's already running into some subtleties in order to make sure that you're not like wasting a lot of qubits on the kind of gauge redundant part of the Hilbert space that's not physical. So yeah, this is, I would say, kind of my answer to that kind of just like falls into this general question of alternative formulations that I mentioned at the end. If there was, yeah, there are clear difficulties that exist in going from in the standard Hamiltonian picture and going from that to quantum algorithm. So it might be that looking at, let's say, the path integral in a different way might give us a more efficient way forward. But yeah, I don't entirely know what it is at the moment.
Also, I can add that the path integral Euclidean, because the Minkowski doesn't make any sense. It can only answer certain questions. It doesn't answer any questions related to real-time dynamics, except by an act of fate, right? That is analytic continuation from imaginary time to real time. You cannot compute transport coefficients. You cannot compute a lot of things, right? So it works when it works.
Is there a way to like reliably quantify the error from that decoherence noise that you were talking about? Like if you do a measurement and you see from sort of like your noise injection that it does have an effect. Like in that case, you had like an actual, expectation of what you're comparing to. So you're like, aha, I see there's difference. You know that there's
Reliably, no. Because what's real, I can say kind of what's actually happening when we do our zero noise extrapolation is you can really what we're doing is if you take a C naught operation, tangling operation, and you run it through two C naughts cancel out. It's C naught squared is 1, and so what we do is we take our system and we artificially boost up the noise by replacing certain places where C naughts appear with 3 C naughts in a row, which ends up making the circuit completely equivalent, but increasing the amount of noise. And then kind of we blow up the noise in various parts. We take the average, all of that, we extrapolate to zero noise. So yeah, I think none of this really is particularly rigorous. It's a little bit heuristic. Certainly, even if that part of it you could make rigorous, which I think actually doing a more careful analysis of exactly what the asymptotics of that look like is something that we could do if we really wanted to. But the thing is that even doing that, what it would do is it would I think reduce the noise from decoherence from 2 qubit interactions. You would kind of, well, not reduce, it would extrapolate down to the zero noise limit of 2 qubit decoherence interactions, but multi-qubit interactions, it's not saying anything about. And for large enough systems, those you would expect to be smaller, but for large enough systems, just the combinatorics of those become worse. And so at some point, at some point that is going to also be a significant source of error. So yeah, so I would say kind of what we're doing right now to mitigate our noise is very much an ad hoc procedure that I suspect would not scale up well to large systems, and we will need to work out something better. I would say, but on top of that, I would kind of make another comment, which is that at some point, it's not clear how long it's going to take us to get there. When we get systems that are stable enough and large enough where we can implement quantum error correction, this whole discussion of noise is going to just become qualitatively different, because right now what we're doing is we have no way of actually protecting against decoherence. All that we're doing is kind of trying to pack our calculations into a small enough amount of time that we can run it before the whole system just falls apart. But once you're able to do quantum error correction, then you will actually have the ability to dynamically stabilize your system in the middle of doing all of these manipulations. And then at that point, much like we don't worry about physical bit flip errors in our classical computers, because we have ways of like averaging over a whole bunch of bits such that those become exponentially small. We're going to have ways of stabilizing our system such that we can make the sort of noise, the sort of decoherence errors that are really kind of the fundamental limiting factor right now, exponentially small at the cost of making our calculations just longer to run. So to some, which is to say that to some extent that these issues of, I think people are more or less okay with dealing with noise mitigation as an ad hoc technique because it's a placeholder for something that we have to do right now in order to get sensible results, but asymptotically in the future, this kind of error is not going to be a thing that we're really worried about. Yeah.
So since you're considering something that is running on a lattice, seems like it's not the most efficient thing to run it on a universal quantum computer. So do you have some idea about considering the spatial structure to have to run something like on the kind of cellular, quantum cellular automata or something like that? Like something that takes advantage of the spatial structure on the particular tensor structure.
Yeah, so for lower dimensional systems, people have looked at this for like one-dimensional analogs, two-dimensional analogs. Like maybe there's some way of actually designing your quantum system in a way that mimics the geometry of the space that you're trying to simulate. I would say, well, we're not focused on that simply because I think it's a somewhat different approach to the problem. But also I would say that those approaches are more, I would say, a little bit more ad hoc and will depend, will work for certain field theories that you're trying to simulate, and it's not obvious that their lessons are going to translate to others. Particularly once you start trying to talk about real world three-dimensional systems. I don't think there's any way that we like all of this stuff exists in the physical analog systems that people have built have all been like one or two-dimensional systems. I don't think we actually even know how to put together three-dimensional systems with full three-dimensional connectivity. And on top of that, I would say that kind of a picture will work provided that it's obvious that what you want to do is discretized in position space. And it's not at all obvious to me, actually, that at the end of the day, that is going to be the most efficient way of organizing these systems. So I think there's still some utility in trying to work how all of this looks like on a universal quantum computer, because while it might not be the most efficient way of implementing some of these operations in a given system, in a given basis, it does give you the freedom to experiment with arbitrary unitary transformations of your system and seeing what that gives you.
Okay, well, we can keep discussing, but let's thank Marat again.
Stop the recording. Yeah.